Hello everyone. I'm Les Bell. I work for Arm. I've been working on the Arm NN libraries and I've got this presentation now written by me and my colleagues Matteo and Narumol here at the front. So we've got a lot to get through, so we better get on with it. So I'm going to take you through an overview of Arm NN first of all, and then a quick section on using the graph builder in the Arm NN library and optimizing and running the network with Arm NN. And then I think the interesting section for a lot of people is going to be the backends and most importantly how to write custom backends for the Arm NN library, what you have to do and where to put it. So let's start with the Arm NN overview. Arm NN, it's a C++ 14 inference library API for Linux. It's developed as open source software, and of course contributions are welcome from everyone. It uses Arm's compute library, and we also have an Android NN API driver, and releases are synchronized with Arm NN for all these libraries together. There's some useful links there to get you started with all of these libraries. So if you want to contribute, then go and have a look on GitHub. So Arm NN, it's Arm NN fits in the middle there. NN applications have already been written to use some compute library, and those applications can use Arm NN instead. They can also continue to use the compute library. Arm NN also provides, we also provide this Android HAL driver, so that if you're coming through from an Android system, you can use the Arm NN library as well. And Arm NN provides backends for the lower level libraries. So we have the Neon backend, the OpenCL backend. We have a new machine learning backend coming soon. And third parties can add their own backends to the Arm NN library if they want to. But you'll have to do all the work. So just to say this, Arm NN just does inference only, it does not do training. There's an overview of the Arm NN components here. We have the graph builder API here. Generates an internal graph representation of the networks. And from the top, we have TensorFlow parser and TensorFlow Lite parser, the Caffe parser, an ONX parser, and also the Android NN HAL driver, all using the graph builder API to generate the internal graphs for Arm NN. Arm NN provides an optimizer which deals with a few things, and it provides a runtime which sort of controls the backends. And below the backends we have the compute library which provides the backend for the Neon and the OpenCL stuff. And we have our custom backends can be built into the Arm NN here with your custom libraries for your own hardware. There's some of the layers that we support in Arm NN. There's more coming all the time, so, and you can always add your own if we don't support it. You can always provide your own layers. So now we're going to move on to the graph builder. Well, I'm sure many of you are already familiar with this, but graph builder provides step-by-step API for building a complete model. It's sometimes called the model builder. It's got an interface header called inetwork.hpp that's in the Arm NN libraries. And it's got the main classes are the network interface and the connectable layers that the network uses in the graphs. To add a layer to the graph, we got methods such as add pool and 2D layer to add a pool and 2D layer to the graph, and most of the layers take a descriptor to include all the weights and biases and other parameters that need to be added to the layer. And there's similar methods for all of the layers that we support. The layers have to be connected together. They're connected using the iConnectable layer interface, and that defines a slot mechanism. And each layer can have any number of input slots and any number of output slots. The number of input and output slots is generally it's defined by the layer itself. For most layers, it's a fixed number. For some layers, it's a variable number. The output slots can be connected to one or more input slots in a graph, as shown here. So we've got the output slot from layer 1 going to input slots on layer 2 and layer 3. But input slots can only ever be connected to one output slot. So you can't have multiple outputs going into one input. And we're going to go through a simple example graph here with this single additional layer with 2 inputs and a single output. First thing you have to do is to create your network object. And then you have to add your layers to it. And there are 4 layers here. There's the first input layer, the second input layer, the addition layer, and the output layer. Input and output layers have a binding ID associated with them, and all the layers have a name. This addition layer has just got a name. It doesn't have a descriptor or anything. It's just a very simple one. So that code shown you on the previous slide just gives you a graph like this with the 4 nodes in the graph, but there are no connections to it yet. To establish the connections, you first identify the output slot that you want to connect, and the input slot you want to connect it to, and you tell the output slot to make that connection. You do the same for the other output slots to establish your fully connected graph. The last thing you have to do in the graph is to set the tensor information, the shape, the data format, and the quantization parameters. In this example, oops, wrong button again. The shape is defined here. It's just a tuple. The data type we've chosen here is float32. If it was a quantized data type, you would also define the quantization parameters for the scale and the offset. And you simply set the this tensor information on the appropriate output slots. Sorry. Do you want to get the mic?
So what's the layout of the shape? Is it NCHW or NHWC?
Arm NN actually supports both layouts, as does the compute library that it uses.
So is it there a default for this shape? If we didn't mention
the data layout will be defined. It'll either be fixed for the layer, depending on the layers, or it'll be defined as part of the parameters that are actually passed to the layer when you create the layer information. When you actually create the layer.
Okay, so so you mean it support both NCHW and NHWC?
We support NCHW and NHWC.
Okay, okay, thank you.
So once you've created your graph, the next thing you have to do is to optimize it, and then run it. So we have an optimizer object, an optimizer interface which is allows you to the optimizer actually performs basic validation of the network and it modifies the graph for correctness in certain copy layers between the different backends, and we also support as an option floating point 32 to 16 conversions and vice versa. And we also have an option to add debug layers to all of the output tensors in the graph, so that you can get debug information from a graph while you're developing it, and the debug information will be sent to standard output, so that you can actually see what tensors were actually generated at each output. One of the things that we do is when you optimize the network, you give it a list of backend IDs that you want it to run the graph on. This is a list. The first entry in the list, the first backend identified in this list will be chosen if possible, and if it doesn't support a particular layer, then we'll move to the next backend in the list, and so on until we find a backend that will support the graph layer. We have other options in there which will come. I'll just explain on other slides. The optimizer performs some backend independent optimization, such as removing redundant operations. It optimizes permutes and reshapes where possible. And
sorry, I have questions for page 25. So there it says insert copy layers between backends. So if the backends have different memory management, how to resolve this issue?
I'm sorry, I don't understand. The copy layers are just to copy the tensors from one backend's sort of memory area to another backend's memory, so that basically, I'm not sure how to explain it. Do you know, Matteo?
So you mean, so if I have, let's say, one backend with one, say, memory layout and another backend with the different memory layout, because that's actually not supported, if that answers your question.
For example,
because as far as a copylator is concerned, it just does, let's say, a mem copy of a portion of a memory from a backend to a different backend. So it just needs to transfer, let's say, a tensor, the value of a tensor between backends.
If some accelerator has some FRAM or similar memory, not just a DRAM, right? Because for some accelerators in the market, they have some their own memory, for example, SRAM, for performance optimizations.
The backends usually have their own layout for the tensor information, in which they in memory that they allocate themselves. And that is my understanding is that copy layers I just simply copy the tensor information from one backend's layout into another backend's layout, and so that the next backend can actually handle it without having to pre-process it, because we will do all the conversion between the different backend layouts in the Arm NN library. But we can discuss this afterwards if you prefer. If that's all right. Okay. The optimizer decides which backend to assign to each layer, and as I mentioned earlier, it will choose the first backend in the list that was given in the call, and it will ask that layer whether it's it will ask that backend whether it supports the particular layer using an is layer supported interface that must be provided by the backend. If the backend doesn't support it, Arm NN will choose the next backend and ask it that if it supports the layer instead, and it'll repeat until the list is exhausted or we find a backend that does support it. We then have to run some backend specific optimizations. I mean, Arm NN can't obviously understand the backend specific optimizations for custom backends, so the backend itself has to actually support this, and we have an interface to the backend using an optimize subgraph method provided by the backend to actually do this, and there'll be more details on this later. The output from the optimizer is an optimized network object. And if you want to ensure your backend is actually assigned to a particular layer or a set of layers in the graph, then you must, when you optimize a graph, just ensure that your backend ID is the first in the list of the backend IDs that are requested, and make sure that you so that when we call the is layer supported function on your backend, make sure that you return true, and your optimized subgraph call should not fail. If none of these, if any one of these is not true, then we won't use our backend for that particular layer. The next thing we have, Arm NN has a runtime object, which is for controlling the running of the graph. It manages the runtime memory in a basic way, and it executes inferences and predictions using an interface method called enqueue_workload. The enqueue_workload method is it's just a very low overhead dispatcher. It dispatches the workloads to the backend assigned previously, and it manages the synchronization. So to run the inference, the first thing we have to do is create the runtime. So we have a runtime create static method to actually create the runtime object for you. It can take a number of options in a create options structure, and the only options that this supports are some GPU tuning and profiling options that the ARM Compute library uses for the Neon and CL backends. The next thing we do is to optimize the model. So we call the optimize function with the model that we've just created, the backend preferences, and the device spec. The device spec is actually provided by the runtime object using this interface method here, and all it is a set of registered backend IDs. So we've been given a set of backend IDs that we want to the optimize function that you want us to actually choose from. That may actually differ from the backends that are actually available on the hardware. So we have to get the registered backends from the device spec. And as I said, the backend IDs, it's just a vector of backend ID objects, and each backend ID object is just a wrapper around a simple string identifying the backend. Yes, then we have to load the network. We pass the optimized model to the load network method on the runtime. This will generate a network ID, which and it will also return a success failure. The network ID is used later for running the optimized network, and so this method creates a loaded network object and adds it to the runtime. And the loaded network object it will create a list of workloads, which is one per layer, using the backend's workload factory object. The workload factory object, which we'll describe later, is something provided by the backend. So if you and it has methods. It has to support methods like create pool in 2D to create a pool in 2D layer, create convolution 2D for a convolution 2D layer, and so on for all of the layers that you want your backend to support. We then have to create the input and output tensors to pass to the graph. The input tensors, it's just a list of with a binding ID and a constant tensor definition with the data for each of the tensors. And the output tensors is just similar. It's just a list with a layer binding ID and constant tensor for each of the outputs. And then you have to execute the network using the NQ workload call. The network ID passed in is the one that was created on the previous slide when you loaded the network. And you also pass the input and output tensors to NQ workload. And that the NQ workload executes all of the layers in the graph sequentially on the assigned backends that we got when it was optimized. NQ workload blocks until execution of the graph is complete, and the result will be in the output buffer tensors. There is a simple application, a simple sample in the Arm NN source code if you want to have a look at it and how to do this again. So now let's move on to the backends and workloads. So we've got a brief introduction to backends and workloads to start with. A backend is just an abstraction that maps the layers of a network graph to the hardware that is responsible for executing those layers. And backends support one or more layers from the graph, and they may optimize any subgraphs that we create to, for each of the backends and that are assigned to them. They create the backend specific workloads, as we mentioned earlier, for the layers that they support, and they are responsible for executing those workloads. So we've mentioned subgraphs a couple of times already, so it's probably worth explaining what we mean by a subgraph here. A subgraph is just a portion of the original graph that holds a list of layers from the original graph that are contiguous, contiguously assigned to the same backend. It's the largest set of contiguous layers that can be assigned to a single backend. So in this example here, wrong button. We have layer 1 and layer 2 assigned to subgraph 1 because they're assigned to the same backend. We have subgraph 2, which has just got layer 3. It's assigned to a different backend. And we've got layers 4 and 5 in subgraph 3 because they're assigned to the same backend. And layers 4 and 5 may use the same backend as layer 1 and layer 2, or they may not. I mean, but if they do, if they are assigned to the same backend, we can't put them in the same subgraph because they're not contiguous in the graph, and so they have to be handled separately. Workloads. Each layer in the graph is executed using a workload. used to encure the layer for computation in the back-end hardware. It's created by a workload factory, and each backend must provide its own workload factory to create those workloads. A workload factory implements the workload factory interface, as shown here. It's got a get backend ID method so that we can check which backend we're actually talking to. It's responsible for creating the tensors to pass the tensor data into the backend. It must support methods to create the input and output layers, and it must also support create layer functions for every layer that it wants to support in that backend.
So let's go to the previous. What is a subtensor?
A subtensor is a view into a tensor which does not contain all of the values in that tensor. So, for example, a subtensor might it's looking at a larger tensor, and it might have a stride of which is not one. If it has a stride of two, to say just portions of the tensor. We use these in the compute library for the OpenCL and Neon backends in Arm for making more efficient implementations of things like the splitter and merger layers, so that the previous layers can actually use the subtensors to actually the previous layers and the subsequent layers can actually put the data in the right place. And the merge and split layer would then subsequently have less work to do, because it's just a performance improvement for us.
Got it.
Just okay. All workloads need to implement the workload interface, which is very, very simple. It only has a method to execute the operation on the back-end hardware, which would involve reading the input tensors and writing the results to the output tensors. So it's the workload interface classes defined like that. Say this, apart from the virtual destructor, it's just got the one method.
Yeah, for this execute method, is it synchronous or asynchronous?
It's synchronous.
Okay, thank you.
So now we'll move on to how to write your custom backend. Arm NN allows adding new backends through what's been referred to as the pluggable backend mechanism, and you can have them built into the Arm NN library by providing the appropriate source files and make files in a separate directory of under the Arm NN source backends subdirectory in the Arm NN source tree. We use the CMake build system for this, so you have to provide the appropriate CMake files. In the example here, oops, I keep pressing the wrong button. You can create a directory called My Backend in the Arm NN source backends directory, and provide your backend.cmake file for that. The backend.cmake file has to have this add subdirectory command in it, and a list of a list of the Arm NN libraries which you add your backend to it and your backend workloads, and a list. We have a similar list for the unit test libraries there, where you add your backend unit tests to that list. Your CMake lists text file, which you have to also provide, must provide the rules to build these three libraries that we've mentioned here, the my backend workloads and the my backend unit test libraries. So you need to provide those rules to build that. On Android, we use the native Android build system, and that uses you have to create a makefile with a called backend.mk in your subdirectory, and you just have to add the backend sources. You list all your CPP files to be built as part of the Arm NN shared library, and for example, you would add your source files like that. And we have a similar definition for the test sources, and you just add your test sources to it, and those files will be automatically picked up by Arm NN's main Android makefile. So here's a directory tree structure showing we show the CL backend that we have for Arm NN's for the OpenCL support, and the Neon backend. They all have backend.cmake files, backend.make files, and cmakelist.txt files. If you want to have a look at those to help you figure out how to define your own, you basically just add in your own directory here with similar files. There's a README file which covers most of the stuff that I'm going to be talking about for the rest of this presentation. We have our reference backend here as well. The backend's common directory contains some shared code that the CL and Neon backends use. Yeah, you don't have to call your backend my backend. You can choose your own name for it, because it would be silly if everyone called their backends my backend. Okay, so all backends must be uniquely identified by a backend ID, and you create a backend ID. Just the backend ID, we have a class for it. It takes a string as the only constructor parameter, and it basically just provides a simple wrapper around that string. The name that you choose for your backend must be unique amongst all the backends built by Arm NN. And we must register the backend with the Arm NN library. So we have a backend registry class, and you obtain there is a single instance of the backend registry class which you have to obtain using this function here, and you register by calling the register method on the backend registry with your backend ID and a factory function to create an instance of the workload factory object that you have to provide. We can register backends statically using a static registry initializer structure that we have defined. And this example here shows the static registration that we have for our reference backend. You define your backend ID here. The name for your backend is CPURF, and this is just wrapped in a simple function call because it's constant expression. We wrap that backend ID, wrap that in a backend ID, which is statically defined again, and we've put a function call around it to actually, because just make a static access to it easier. And this is the static registry initializer. We just declare one of these with our registry instance, our backend ID, which we get using the function we defined up here. And the factory function is just a lambda function here, which returns a new instance of the reference backend object in this particular example. So all backends need to implement the backend internal interface. And the backend internal interface just supports these methods here. First one, create memory manager, which will just to create your memory management object, which we'll talk about in a little while. Is the workload factory, which I've got more information on in another slide in a moment. The backend context, which we've also got another slide on, an explanation of that. The get layer support, which we already mentioned, it provides the is layer supported functions for all the layers that you actually support in your backend. And the optimize subgraph function to do the subgraph optimization if you have any that you can support. The output from the optimized subgraph is a valid optimized subgraph and a flag to indicate that the optimization has been attempted. The flag is passed in as an output parameter. And previously, in previous versions of Arm NN, we had a get optimizations function call for the backends, but that's now been deprecated because the optimized subgraph is much better. So let me remind myself what's on this slide. Yeah. In the optimized subgraph, yeah. In the optimized subgraph call, oops, wrong. You get past the subgraph that has got the contiguous list of layers that are being assigned to this backend, and the optimization attempted output parameter. If you don't do any optimization, if you don't want to do any optimization, or there is no optimization you can do for this particular subgraph, all you have to do is set the optimization attempted flag to false and return a null pointer, and Arm NN will just use the subgraph as it is and make the appropriate calls to the workload for each of the layers in the subgraph as they are. Examples of the optimizations you can do, or for example, you could merge layers for more efficient execution. For example, if you had a convolution followed by an activation, or that you could possibly merge into a single operation, you might want to replace those two layers with a different layer. It returns the optimized subgraph, and if optimization was not attempted, as I already mentioned, the subgraph is not changed and Arm NN just leaves it. If the optimization failed or it was invalid, it's returned null pointer, then Arm NN will reassign that subgraph to a different backend instead of this one, so we can still actually run the whole graph. But if the new subgraph, the new optimized subgraph is valid, and then Arm will actually replace the original subgraph in the overall graph with the new optimized subgraph So, as I already mentioned, you can create new layers when optimizing a subgraph, such as for merging two layers together, or even potentially just replacing the whole subgraph with a single layer. And because ARM does not actually know what optimizations you want to do and what layers you want to merge together, and it obviously can't support all of those, all of the new layers that every backend might want to create. So we have what we call a precompiled layer instead, and a precompiled layer allows any new layer that the backend wants to create to be supported through Arm NN. It holds a pointer to an opaque layer object, and that opaque layer object is responsible for storing all of the information that your backend needs to create that workload to actually support this new layer. The backends must support the workload factory for the backend must support the create precompiled method to create a precompiled layer that Arm NN does understand to actually store this information, and there is a precompiled descriptor that is passed to this method, and the backend must just it must replace the merged layers or in the subgraph that it's given with the precompiled layer that it creates here, and return the optimized graph to Arm NN. Next thing we have is memory management. The memory management model in Arm NN is very simple. The purpose of the memory management is to minimize the memory usage for running the graph, and so the idea is that the memory management will just allow us to allocate the memory just before it is needed and to release it as soon as possible afterwards. So all backends must support the backend internal interface create memory manager method, and this returns a unique pointer to a memory manager object. You would implement your own memory manager and just support this interface. So you would just return an object with your own memory manager object. If you don't want to support memory management, then you can just return a null pointer, and we won't actually pester you with memory management calls. The memory manager interface just defines two methods to be implemented by the derived class for the backend. These are acquire, which is called by the loaded network before the model is executed, and it is when we call the acquire method, you need to allocate all of the memory that you need for running the inference. The second method is release, and that's called by the loaded network when it's destroyed, and the model is no longer required. And when we call that one, you simply free all of the allocated memory that you have. I would recommend you have further internal memory management to optimize memory usage built into your own memory manager. For example, you might want to reuse tensor buffer memory internally when tensors are no longer used within the subgraph that you're given. And unfortunately, Arm NN can't help you with that. Although we do these things in our own backends for the OpenCL and Neon backends.
Yes. So just mentioned. So I'm here. So, yeah. So do you support different memory types right? Because I think for CPU, GPU currently it's okay, since because you are sharing the memory, right? You're sharing DRAM for the acceleration, right? But for the new NPU or maybe ASIC similar IP, they probably have some specific SRAM or internal buffers for such kind of things, right? In this case, we do need some memory allocator for this part.
Yeah, when workloads are created, you have to create the tensors for them. Let me find it. The workload factory is responsible for creating the tensors for your internal memory handling, and you would when we call these functions to create tensor for each layer when we create the workloads, and you would basically have to handle. You'd have to know when if the memory you want to use for the tensors is internal memory for within your backend, then you would do the allocation of that internally then.
Yeah, because for example, we can call it just a device memory, right? So
yes.
and the host memory, right? We do need to handle the copy. Just as you mentioned, we can insert some copy layers. We can use DMA to do
the copy layers.
Yeah.
Copy layers will actually call the create tensor handle to create the tensor information that it needs for where it wants to copy the memory to, copy the data to. Sorry, and if your create tensor handle is actually allocated internal memory in your device, then it will be copied into that internal memory.
Okay. Yeah. Maybe I needed to dig into the implementation to understand more. Okay.
Yeah. I'm not an expert on this particular part of it, so
okay, thank you.
But that's my understanding.
Yeah, because I asked this because for the NPU accelerators, it's a very common case, right? For some memory control for the device memories, right? Yeah, it's very common.
Yes, and our OpenCL and Neon backends as well. They actually have their own memory space that they deal with this internally as well. So. That's why we have copy layers, one copy in between different backends within the same, even though they're actually part of the Arm library already.
Yeah. So if we can have several pages to describe this, how, for example, how to handle the device memory in Arm NN, I think that can be helpful for other companies to add their accelerators into this Arm NN framework.
Yeah.
Right.
Yeah. Okay.
Okay. Thank you.
Where did I get to? Memory management. Okay. Yes. Yeah. So that's basically it for memory management. Anyway, we just have the acquire and release, and you have to do anything more clever than that. You have to do yourself. And yes, the backend context. This is the last thing in the workload interface that was mentioned. You can, if you want to support this, this is basically just provide some callbacks for us to tell you when things are happening. We will call the before load network method and after load network methods just to let you know that we're about to create the network and we're finished creating the network. And also we can do the same when we unload the network, and with the before unload network and after unload network calls. I was told to ask the question, is this useful? I mean, we don't use it ourselves, but we added it because we thought it would be useful potentially for third-party developers. So if it is useful, let us know.
I think it's useful because we can do some device initialization in this backend context.
Yeah.
Yeah.
Yeah, that's the idea. I mean, so you can do whatever sort of setup that you need and tear down at the appropriate points. So help your internal sort of memory management and whatever. And that's the end of the presentation. Any more questions, please?
So for the memory copy layer, is it inserted automatically by the Arm NN optimization?
Yes, and then we insert the copy layers between the different backends.
Okay.
Yeah.
It's automatically.
Yes.
Okay.
So when you use the CPU backend, can you restrict the number of CPUs, or does it automatically just excuse me, use all the CPUs on the system? How does it work?
Our CPU backend, it will just use whatever's available. These layers are only run one at a time, so it'll only be using one CPU at a time anyway. So.
Okay, thank you.
Any more? Okay, thank you very much, everyone.